Hello, I am Luca Cardelli from the University of Oxford. I will talk about the Kaemika app for integrating protocols and chemical simulation. Kaemika is available on all four major app stores. It provides simulation by ordinary differential equations and by linear noise approximation of both chemical reaction networks and digital microfluidic protocols, a novel graphical representation of reaction networks, functional monadic programming for internal scripting, and of course a graphical user interface. First, let's look at the chemical reaction sublanguage. The simulation techniques here are fairly standard. What's novel are the program abstraction facilities and the uniformity of the techniques which are available. For example, program abstraction can be applied to any chemical species or subnetwork, and stochastic simulation can be applied to any kinetic model one can write, that is, without any of the usual Gillespie algorithm restrictions on kinetics. This is the Windows version of the tool. There are three panes with menus on the sides. We can select examples from the tutorial. On the left pane, there is a script, which is, in this case, a Lotka-Volterra oscillator. Initial values are drawn from uniform distributions, and two species are initialized, X1 and X2, standing for prey and predator. These are three chemical reactions in standard chemical notation with the rates here. The report statement determines which species are being plotted, and the equilibrate statement determines how long the simulation will run for. So clicking the play button starts the simulation in the top right panel. Every time is slightly different because of the random initial values. We can inspect the simulation by hovering the mouse over the plot lines. And we can also choose which lines to show from the legend. The random initial values are shown here. They can be locked in place, and then they will not change until they're unlocked. In the bottom right panel, there is a representation of the chemical reaction network, which I will describe shortly. The graphical representation can be replaced by a textual description of the kinetics and the reactions. We can activate stochastic simulation from this menu, and we can show mean and variance, and also various statistics like the Fano factor. We can also look at the equations of the differential equations and of the LNA for the covariances. Now, about the graphical representation, chemical models are produced by scripts, which can be highly parametric and hard to read. So it is nice to have a way of seeing the networks graphically. Unfortunately, automatic graph layout for CRNs is messy. It does not scale up well, and often has symmetries that would be helpful. So I came up with a new graphical representation. Instead of drawing a reaction graph, we have a reaction score, which is kind of like a musical score. In a reaction score, species are drawn as horizontal score lines, and reactions are drawn as chords between the lines. So, for example, the reaction A plus B equals C plus D, A, B, C, and D are the score lines, and the reaction is this interconnection between the lines. The other examples here are simply special cases of that situation. In addition, we also have a compact way of representing catalytic reactions. This is similar to what we've seen before, but is drawn as a connection from a catalyst to a transition between species, like in the case of the reaction B plus A equals A plus C, where A is the catalyst. And the other examples here are, again, special cases of that situation, including autocatalysis. Now, this representation of CRNs is complete, meaning that any CRN can be laid out this way, and it's also unambiguous, meaning that the original CRN can always be recovered from the representation. Here is a larger example of a reaction score. There are 16 reactions, and they look like this. With a little bit of reordering, you can bring out some symmetries. You can see this subnetwork is the same as that subnetwork, and also these four reactions are kind of repeated down here. This can be compared with the same exact network as laid out by GraphViz, where it is hard to see any symmetries, and it's also hard to arrange it to bring the symmetries out. It is even hard to look at a single reaction in the graph because you need to visually trace edges across the whole graph, while in the score, each vertical slice is a reaction. Now, back to the modeling language that produces those reaction scores. Models can be generated by programs that freely contain both chemical reactions and control flow. There are rich data types, numbers, chemical species, functions, networks, lists, and flows, so a combination of standard and domain-specific types. Flows are composable functions of time used in rates, in plot trajectories, and in programmatic observation of the results of a simulation. The programming model is based on modern abstractions. It is functional. So functions take data as parameters and produce data as results, where data are all the things above. Networks take data as parameters and produce effects as results. So in this respect, the model is monadic. There are effects. Effects involve the creation of new chemical species, the generation of chemical reactions, and also the execution of protocol steps in protocols. And the model is nominal, which means that the chemical species are lexically scoped, so they're not strings, they're proper program variables, and an unbounded number of species can be generated. So a program can produce a chemical reaction network whose number of species and reaction is unbounded and depends on parameters. Just one example to explain all of that. This is a function called predatorial that generates a stack of lockable Terra systems, where each predator is the prey for the next level up. It is parameterized by the number n, which is the number of stacks of predators. If n is equal to 0, then actually there are no predators, there is only a prey species with some initial value. This reaction says that the prey reproduces. Report means that we want to plot the prey species. Yield means return the prey species from the function. Now if n is greater than 0, then there is a predator, and the prey for that predator is the result of predatorial at the previous iteration, n-1. These two reactions are the reactions for lockable Terra, say that the predator eats the prey and reproduces, and the predator dies if it doesn't find enough prey. Again, we report the predator to plot it, and we yield the predator to return it from the function. In the end, if we call at the top level predatorial of 5, then we produce 5 stacks of predators, and the top level predator is the apex predator, which is returned by this invocation. Equilibrate means that we're going to simulate the system for 50 seconds. Now, if we do that, then we see that in red, the prey is subject to a lot of stress, but so are most of the predators, and at the bottom, the green one is the apex predator that is also the lowest concentration. Again, you can see here the stack of predators in the score representation, and this is the example. So now we're going to discuss the protocol sublanguage and the related microfluidics simulator. Samples are containers of chemical species, for example, test tubes. A sample is characterized by volume and temperature. It contains a specific set of species with given concentrations in the given volume, and it evolves according to a set of reactions which may depend on the temperature. Each sample is isolated from other samples until they are combined. Protocol operations accept samples, use them up irreversibly, and produce new samples, so samples are used in a linear or affine fashion. Here is an example of a protocol. There is a species C, which is global, meaning that it can occur in multiple samples. Sample A has a volume and a temperature. It contains the local species A and some amount of the global species C. And there is a reaction connecting A with C. And we equilibrate, we simulate this sample for 100 seconds, resulting to a new sample A1. Simulate the sample B with some temperature and volume, and some reactions in this sample, and we simulate this for 100 seconds, resulting in sample B1. Now here are some actual operations. Here we split sample A1 into 2 parts. In this case, this means 50%. So we get 2 samples C and D, and we immediately throw away C, we dispose it. Next, we mix D and B1 to form a single sample E, and there is a new reaction connecting A and B in the mixed sample, and we finally equilibrate E for 1000 seconds to obtain the sample F, and then we dispose of F. Now there are 3 equilibrate statements in this protocol. So if we run the simulation, we actually run 3 simulations. So the first time we get a simulation for the sample A, and then the simulation pauses, and that's the reaction in sample A. Then the second time we get the simulation for sample B, and the third time we get the simulation for sample E, which actually contain 3 reactions, and the 3 reactions altogether now form an oscillator. Just for reference, here is an actual chemical protocol from a protocol database and how it translates into Kaemika. Without going into details, it prepares a buffer by mixing and heating several chemicals. In the end, every invocation of the makePBS function produces some amount of this buffer, which can then be used in other contexts. So now, given that we have this protocol language, the question is, how can we execute it? We can imagine compiling these scripts to instructions for liquid handling robots that manipulate test tubes, or compiling them to ad hoc or even general purpose microfluidic chips that can carry out mixing and splitting with microchannels and pumps, or even compiling them to instructions for lab technicians. But another very interesting, very general way is what's called digital microfluidics. This is a general and programmable platform for executing liquid handling operations without relying on fixed equipment topology. It's an evolving technology which has been demonstrated also to support a number of automated observation techniques such as sequencing and mass spectrometry. Here's how it works. This is OpenDrop, which is an open hardware platform where you can in principle download the schematics and build it yourself. It's an array of electrodes that, by modifying electric fields, can cause little droplets to move around and can both merge and split the droplets and route them into different positions. Kaemika supports a digital microfluidic simulator. This is the same example we saw earlier, but now we can activate the simulator. And now when I run the script, then the operations, the liquid handling operations now do something visually. And as you may notice, as I click the simulation here, it's interleaving the simulation of the protocol with the simulation of the chemistry. So it's now simulating part of the protocol. And when this stops, I can proceed and activate the next simulation. And now the next operation starts, and then the chemical simulation starts again. The digital microfluidics simulator implements the operations of mix, split, equilibrate, and dispose. The equilibrate is actually moving the droplets from a cold zone to a hot zone where the chemical reactions can actually happen. Then the chemical simulation happens there, and then the droplets go back to the cold zone where basically the chemical reaction is supposed to be frozen. And all the routing is automatic. There is nothing in the script that tells you where the droplets should go or what they should do. This is all compiled out into routing for the droplets. We have seen in the previous sections chemical simulation and protocol simulation. The big picture is that Kaemika programs contain both the model and the protocol in a unified description. This is interesting because normally a model says nothing about the protocols used to test it, and conversely, protocols usually say nothing about what models they're testing. But if an experiment fails, then you're bound to ask whether the problem was in the model or in the protocol. So we really want to have the two things together, particularly if you're doing some kind of statistical inference, because then there are always going to be uncertainties in both the model and the protocol. So unifying these descriptions is important for automated execution and automated analysis of experiments. Now I'm going to show how to extract the model and the protocol from the script. We simply go here and we select show protocol to see the protocol. These are the protocol steps with none of the chemistry, just the liquid handling manipulation and the setup of the test tubes of the samples. And also you can go to show equations, and this, for each state of the protocol, it shows you the state of each sample, and it shows the kinetics for all the samples. And this, for each state of the protocol, it shows that kind of information. So in fact, this is a hybrid system going through all the different states. It's also possible to extract at least the protocol information as a graph, and this is split out into graph-viz format for rendering outside. In conclusion, we have discussed the notion of integrated modeling of reaction networks and protocols and how the Kaemika app supports it. The goal is to eventually close the loop of modeling, experimentation, and analysis by automation. This promises to revolutionize scientific progress. At the moment, this is only possible in some specific areas, but once the technology is bootstrapped, it will become applicable to wider and wider situations. The Kaemika app aims to stimulate this bootstrapping by delineating what is possible. Thank you very much.